Hello, it's Monday the 3rd of July 2017. I'm Dave Rothery, Professor of Planetary Geosciences here at the Open University. I'm also the Chairman of our Level 2 module S283 Planetary Science and the Search for Life. And this is a little video just to introduce the course to you if you're thinking of starting it, or even if you already signed up, just to show you what to expect. So I'll turn this camera around now so I can show you a few things. So okay, here's the course. It's based on books. I should put them this way around because that's the second book. This is the first book. These are books that we co-published with Cambridge University Press. This is the meat of the course, but it's supported at every step by the module website, where we guide you through what you should be doing on each week. There's a new chapter to look at every week or so, and the assignments can be met by clicking on the assessment task. These TMAs, 4 tutor marked assignments, they're your passport to the exam. You have to get 40% overall in the TMAs, and then you're allowed to sit the exam. And you, of course, will also be supported by an AL, Associate Lecturer, your own tutor. And there's quite a lot of discussion on the website as well. The forums, this is the website you will be using, so the forums are empty at the moment, so there's something to show you there. But there are news items that we post because planetary science is changing all the time. There's news breaking. I mean, here's a piece about plumes on Enceladus and Europa. This is news that we put up in April. Oh, okay, that was me. I was on Facebook Live with the BBC. Organisms have primary producers, the things that drive any. So we put links to stuff like that. That was when eruption plumes had been discovered on, or confirmed by Hubble Space Telescope on Jupiter's moon Europa, and that's very relevant to the second book of the course. Let me take you through what's in the course. Introduction to the Solar System. That's what it says on the tin. These books, by the way, are revised editions, came out in 2011. It's moderately up to date. We are working on future revised edition, which will come out in 2018. We might be able to put some proofs of that for you to look at, but what we're teaching is based on the current edition. So there's a tour of the solar system, introduce you to various bodies in the solar system. We'll look at the internal structure of the terrestrial planets. By the way, this is a course that if you've done any level 2 geology, some of it you will find familiar at the beginning. And if you are doing level 2 geology or have done level 2 geology, this is an excellent course to go with it, because if you're studying the geology of the Earth, I mean, you're missing a trick if you don't equally well study the geology of other planets. And having done S111, or if the older course S104, the Introduction to Science courses, you will have met some plate tectonic stuff, so some of it will be familiar. The other thing about the course 283 is it's a natural course in the pathway Astronomy and Planetary Science. Our sister course S282 is another 30 credit module for you to study alongside, or either before or after. So here we're still looking at processes inside planets and surface processes, impact processes. Here's the impact crater in Mexico. That's probably helped wipe out the dinosaurs. And we look at meteorites. We look at atmospheres of planets. First, the terrestrial planets, that's for its circulation. We go on to the interiors of the giant planets. Some of this has been revised very recently as a result of Juno, a probe that's orbiting Jupiter. Some very exciting results there. Minor bodies of the solar system. Here's where we teach about orbits, elliptical orbits, asteroids on this page. There's some comets. We have members of the course team who were involved in bouncing around on Comet 67P that Rosetta visited. Introduction to the solar, how the solar system formed here. Meteorites, because they can tell us an awful lot about the early solar system. Meteorites, a record of formations, that final chapter. So that's the first book, takes you through half the course. The second book is an introduction to astrobiology. This has origin of life, And I guess if you're following a geology pathway and are studying S283, which is a 30 credit module, geology level 2 S209 is 60 credits, you'll need another 30 credit module to go with it. So you either will be doing astronomy, or the only other 30 credit course in science, at least, that's relevant is for biology of survival. So if that's the route that takes your pick, then there are ways to combine useful courses. What is life? How does it begin? The Miller-Urey experiment, habitable zones around stars, and how that concept is a little bit out of date. Now we realise there can be life underneath ice. Then we talk about Mars, layered structure inside Mars seen from radar, Mars surface seen by landers and rovers. There's good geology structures here seen on the ground. And then we talk about icy bodies, mostly Europa and Enceladus. So I'm just flicking by the smaller, less active icy bodies. Interior structures of Jupiter's moons. Here's Europa. Here's the body where we think this ice beneath the surface has an ocean which is exposed when the cracks open and so on. And there's a wonderful potential habitat down there inside Europa. And here are plumes of where the ice surface on Enceladus, a small moon of Saturn, is ruptured, and those plumes erupt into space there, show there's an ocean below the surface on Enceladus as well. So Enceladus and Europa, the two most habitable bodies in the solar system beyond the Earth. And then we look at Titan as well. The lakes of methane on Titan's surface here seen by radar, wonderful features. We've got a cycle of evaporation and precipitation involving methane, which mirrors the hydrological cycle on the Earth. Then we go on to exoplanets, planets around other stars, how you can detect them. We concentrate on transits. When a planet goes in front of its star, it causes a dip in its brightness, very minor fractional dip in the brightness, but that's one way to see a planet's transiting a star. There's also changes in radial velocity. As the planet goes around the star, it swings the star to and fro, so you get a Doppler shift. So those two methods of detecting exoplanets are the main ones. We've got statistics on exoplanets. Now this dates really quickly because we're getting 1,000 new exoplanets every year. But it's a fascinating topic, how to find life on exoplanets. That's the point. We know now there are planets around most stars, and some of those are in habitable zones, however you define habitable, and some of these will be places where life could begin. And what we don't know, the big question is, if you have the right conditions, will life start, or is life on Earth an incredibly rare event? And that's why we want to study exoplanets, to find out if there is any life there. A little bit about finding and communicating with extraterrestrial intelligence, and that's the end of the course. Let's turn this round now. Do enjoy it, do have a go. It's a good course, good fun. The students seem happy, they chat to each other on the forum. I'm now going to go around the School of Physical Sciences and introduce you to some of my colleagues, and in particular to the module team, because we're meeting today to deal with this year's exam. So this is the Robert Hooke building, where most of the School of Physical Sciences is based, though not we planetary surface people. So let's go in and see who I can find to show you in here. We have quite an interesting foyer here. I mean, here is, I think, an actual size model of Philae, the probe that landed on the surface of Comet 67P. I mean, here's the actual comet. So that had a mass spectrometer on board at the Open University. Here is the Rosetta spacecraft itself. This is Philae still attached to it in this model here, big solar panels. And there's actually an iron meteorite that anyone can come in and fondle, and there's some nice stuff on display here. So we're working quite a nice building. Michael, good morning. You're on camera.
Oh,
would you like to say hello to next year's S283 students?
Oh, well, yes, I would.
Who are you and what do you do?
I'm the curriculum manager on S283. I've been at the Open University for many years now, and I really hope that the next presentation goes smoothly. I'm sure it will. I've got an exciting lineup of TMAs for you, and all the very best for everyone. Cheerio.
Thanks. Who are you? What do you do, Ian?
Well, me, I'm just currently sitting reading through my emails, as one does first thing on a Monday, and finding out all the things that one has to do and that one hasn't done.
But today's a big day for S283 because it's a module review panel and we're going through the exam, aren't we?
We are indeed.
Yeah. But when you're not administering exams with us, what do you do planets-wise? Or comets-wise even?
Yeah. I have my history, my background is in, in geochemistry and geology, earth sciences, but I became an instrument builder and was very keen on doing some sort of, I got bored with getting wet in the field, so I wanted to carry on doing geochemistry, but wanted to do something that was wholly lab-based, and switched to studying meteorites and lunar samples, which are absolutely fascinating, I have to say, and I still find that the same now. But with the skill of instrument building, which I learned to study some of those things, I latterly started making instruments to go out into space, and so we've had a couple of instruments that have gone out. One on the Beagle 2 spacecraft, which is, as we know, on the surface of Mars in one piece. And we also built an instrument that landed on the surface of Comet 67P.
Three times.
As well,
because it bounced.
As part of the Rosetta mission. And again, that's still there in one piece.
Yeah. So we're in a meeting room waiting for the exam papers to be delivered so we can adjudicate borderline cases. But meanwhile, here's Manish. Manish, what do you do, and what do you do on 283 as well?
So I'm a senior lecturer here at the Open University. I work on space exploration. So I build instruments to go to Mars, to go to Titan, figure out what's going on there in the atmosphere, on the surface. And ultimately that feeds back into the stuff you guys are learning on S283. So your Mars chapter is informed by the instruments we build and send to Mars. Your Titan chapter is informed by the instruments that we send to Titan. So ultimately, we're doing stuff for you guys at home to learn about at the cutting edge of science.
I'd say something about Trace Gas Orbiter, which is orbiting Mars right now.
Yeah, so this is our current mission, is the ExoMars Trace Gas Orbiter. It launched last year, and it's at Mars now. And its plan is to look at the atmosphere of Mars, look for methane in the atmosphere of Mars, and try and figure out where it's coming from. Is it due to life? Is it due to rocks below the surface? What's going on in the atmosphere?
Perfect instrument for this course.
Absolutely. Yeah. You'll be hearing about it in future updates, I'm sure.
Well, I've now come to the Mars yard, and here's my colleague from S283, Suzanne Spencer. Suzanne, talk to the S283 prospective students.
Hello everyone. I hope to see you on the course, and I am personally a Mars researcher. I work on the Curiosity mission, and I have looked at Mars since my PhD actually, and for S283 I'm also looking after Mars and whatever there is to do with the red planet, with life, with astrobiology, and the really cool and interesting things. And here we are, by the way, in the Mars yard, and that's something that you could see and experience if you go on and study the S818 master module with us in a few years' time, because what we are doing here and with this rover and all the sand around me is we are simulating a mission to Mars. And the students on S818 then get to experience what it would be like to drive a rover such as Curiosity or maybe one of the MER rovers on Mars as a scientist. But for you right now, it's learning everything about the red planet, about the water that was there, about the meteorites that we have from there, and really getting your teeth into, could there have been life on Mars? If so, where would we find it? How would we go about looking for it? And that's what I love about S283.
Now, you may have come upon me before if you studied the Open University Future Learn Moons MOOC, this free massive open online course, MOOC, about moons. That runs in end of October and February every year for 8 weeks. It's free, or you can upgrade if you want a special certificate. So I've been running that for the past several years now, You may also have come upon me through books like these, Very Short Introduction to Moons, Very Short Introduction to Planets. I mean, if you want any pre-reading before S283, I mean, this book is $7.99 or something in the shops, very cheap. That would set you up well. But the course is self-contained. You don't need to read anything else during the course other than the materials that we provide. We expect you've done Open University Level 1 Science. There's some mathematics in it, inevitably. I mean, here's an equation on this page. For example, so you haven't to be scared of maths, but it's not that complicated, and you can skip by it if you really have to. You'll pass the course, but not very well. So if you do take this course, I hope you'll enjoy it, have a good time. It's a fascinating subject, and we're here to help on the forum. Leaving my office, this is what you'll see, because I'm working on the European Space Agency mission to Mercury, Bepi Colombo. It's launching in autumn 2018. This is a mosaic of images of Mercury. I have PhD students working on mapping the planet geologically. We also have PhD students working on Mars, both surface geology and Mars climate. Let's see who's in here. Oh, lots of PhD students, even though it's a Monday morning. Rian, you're working on Mars's atmosphere,
yes.
Climate modelling, aren't you?
Yes, I'm modelling dust storms in the atmosphere of Mars primarily.
Okay, great stuff. That's relevant to S283. Thank you. Chris, what are you doing? Well, I know what you're doing, but these students don't know what you're doing.
So I'm making geological maps of part of Mercury, so the Derain quadrangle.
Derain, who was a French artist.
Indeed, yeah. French impressionist, much like the map.
Better be more than impressionistic when you finished it. And Jack, you're also working on Mercury.
Absolutely. I'm just getting Mercury loaded up now, but I hope to produce a map just like Chris and just like these ones you see on the wall here of the Hokusai quadrangle on Mercury, so the Japanese woodblock artist. And his great wave features on the front of which book? Which OU course?
Oh, yeah, Hokusai is the name given to the quadrangle that Jack's mapping, but he's also, his most famous picture is on the cover of S283 Volcanoes, Earthquakes and Tsunamis. I better cut that into the video now so people can see it.
Absolutely.
Okay. And what's good about Mercury? Why is it an exciting planet, Jack?
Mercury is an exciting planet for a couple of different reasons. It's the smallest planet in the solar system and closest to the sun, and so it's sort of far away and difficult to study. So only 2 spacecraft have ever visited the planet, so we know comparatively little about it. But what we do know is that it has a very large iron core, and it's generating its own magnetic field, which is quite unexpected for such a small planet. And more recent discoveries have included volatile components, elements and compounds that evaporate into space whenever they're heated up. And it's unexpected that these would be on the surface of Mercury because it's so close to the sun, and yet we see these things generating hollows and other interesting landforms on the planet's surface. So it's very mysterious how it's managed to hang on to these volatile elements.
Yeah. Thanks, Jack. It's a strange planet, that's why we do science. And Francis, you're working on Mars. What's so good about Mars?
Well, I study glaciers on the planet Mars and evidence that they might have melted in the recent past. And that's really cool because we think that Mars at the moment is pretty dry. So looking for evidence of water on Mars is important.
And the glaciers are near the equator rather than near the poles, aren't they?
Yeah, well, they're about halfway between the equator and the poles, so in the mid-latitudes.
How does that happen?
So basically Mars at the moment is tilted about the same angle as Earth. So we have a similar configuration of ice, we have polar caps, but Mars tilts quite a lot over geological history. And when it tilts quite severely towards the sun, that ice moves from the poles down to the mid-latitudes. And that's when we think that these glaciers formed.
Great.
Yeah.
Thank you. Right, here's Jack's preliminary map. It is the Hokusai quadrangle of Mercury, and as Jack has just said, Hokusai's most famous picture, the Great Wave of Kanagawa, is here on the cover of the Volcanoes, Earthquakes and Tsunamis science short module with Mount Fuji in the background. Well, that's it. I'm sure I've gone on for longer than I should. Let me just wind up by talking about how the course finishes, which is with a 3-hour exam paper. That's what determines your grade, really. There are 8 multiple choice questions at the beginning. It's meant to be a fairly easy start. Many of them are based on images of the kind of thing you should have seen in the course. Then you'll have about 2 hours of time left after the computer mark part. There are 8 questions. You choose 3 out of the first 4, which cover book 1 essentially, and then 3 out of the next 4, which cover the second book. So you have to be master of most of the course content, but there are bits of a course that you can avoid answering questions on. The exam questions meant to be a test of understanding rather than of memory. I mean, here we're asking you, what can you see in this area of Mars? What processes have gone on to shape the surface, for example? And the second part of the question is about, if you do send a rover there, what planetary protection measures should you undertake? And planetary protection is an important principle about not doing forward contamination, taking microbes from Earth to a habitable place like Mars, or indeed bringing them back to the Earth. So we're after people's understanding of the topics in the course. So it's meant to be a fair test. This year's exam wasn't too much of a disaster. I hope it won't be too much of a disaster for you if you take the course. Okay, bye.